what I'm going to try to do today is talk about the process through which a bunch of data that you have collected or found, or say you're trying to review published work that someone else has done, the process which turns that data into a story. This talk is not going to make you a statistician, but I hope that it will show you the underlying logic of statistical testing. And in fact, we're going to start with what is that and why do we care. And as promised, there is not a single equation in this talk. The trade-off is that there's some code, small amounts of it, and doing, I think, relatively straightforward things. We're gonna talk about a lot of rolling die and rolling dice. There we go. Somebody call a copy editor. A lot of rolling dice and sort of taking random samples and things. So this is the problem that we're trying to address this morning. Is you've plotted, say you plot your data on a map and you're like, wow, everywhere that it's near an oil refinery has a higher cancer rate. And the question is, the headline you want to write is, pollutants from the refinery are causing cancer. Is it justified? And there's a lot of reasons why what looks to be there might not actually be true, and we're going to talk about a lot of those reasons. So we're just going to jump right in. Okay, so some reasons why there wouldn't actually be a story when you think you see something, right? You've plotted your cancer rates on a map. So first of all, this will be up as a video. The slides will be available. The code would be available. So anything that I show you today, don't worry about trying to take down. You'll have it all. These are some basic reasons, right? The first two have to do with what the data actually is, where it came from, what it represents, how it's counted. And the middle two have to do with really the heart of what we're going to talk about today. Statistical testing, why you need it. We're going to spend most of the time talking about chance. In fact, an earlier title for this talk was The Shape of Randomness. I want to give you an intuition this morning as to what randomness looks like. Because randomness doesn't look like what most people think it looks like. Randomness has far more pattern in it than most people suspect, and we're gonna try to show that this morning. And then the last thing we're gonna talk about is generalization, which is very often when you're writing a story, you talk to 5 students, but really the story is about the experience of all students, and those 5 students are standing in for that. So we're gonna say a little bit about when you can make those sort of generalizations to go from the specific to the general. This is one of my favorite slides because it's about as simple a piece of data-driven reporting as you can get. This was actually done by one of my students in a workshop last year. And I trained them to use some basic graphing tools, and I showed them where a bunch of government data could be found, and I said, okay, go find me a story. You have 3 hours. And this is what they came back with. They got data on, this is actually in Eugene, Oregon. I think all Oregon for these numbers. The number of people commuting by bicycle and the number of bicycle thefts. Right, so there at the top is, in the red is the number of people commuting, and in the blue is the number of thefts. And we see the pattern over 5 years. What's wrong with this?
There's a million reasons why bicycle thefts can be going on, right? Is that what you're thinking? Other than just the number of bicycle thefts?
Causation does not equal correlation.
What's that?
Causation does not equal correlation.
Well, yeah, we'll get into all of that. I mean, good. But when I look at this chart, something immediately jumps out at me as weird.
Well, yeah, because if there are more people commuting bicycle, there are more bicycles around, and you would expect the proportional number of thefts to go up the same way if you don't consider other variables.
Right. So commuters are going up, thefts are going down.
Yeah.
What's the label on the left side?
So they're normalized to the starting year, which was January 2005. Just so you can see the comparative differences. So, and you see they're sort of mirroring each other, which is kind of weird, right? And so the student showed this to me and said, I don't know what's going on. The first thing I said is, well, okay, well, first of all, you've got a story, because either this is really happening and it's weird and noteworthy, or it's not happening, which means that something is wrong with the official statistics. So I asked how we could check these numbers. So I'm going to ask you, how would we check these numbers?
Where did they get them to begin with?
They downloaded them from a government website.
Okay.
Yeah. So they are actually police report data for the thefts anyways. The commuting numbers, I'm not sure who collects those.
Yeah.
Yeah.
That would be one of the first things I'd want to know is where's that community numbers.
So congratulations, you have in one question hit upon what it took my my journalism students 10 minutes to get to. So they were talking about, well, we could read the footnotes on the data and compare it with other data sources, and sort of all of this sort of internal consistency stuff. But the first thing I would try is call up the person who collected the numbers.
Right.
Right. So data doesn't come from nowhere. It comes from a person, ultimately, or a group of people. It's collected by somebody for some purpose. And until you understand where that number comes from, you don't understand what your data can or can't say. So you can have unintentional problems, as in, so here's the same type of data, right? Crime data. And in the first instance, the Los Angeles Police Department published this crime map to much fanfare and said, now you can see where there's crime in the city. Only when the Los Angeles Times started pulling in the data feeds, both from the LAPD and from the sheriff's office, it was a complicated process to get it all in one place, and made their own map. They discovered that half the crimes were missing. They don't think this was intentional, the LA Times people. As it says, officials say they're looking into it. It seems to have been just technical sloppiness. In other cases, there's intentional deception going on, or let's say counting that favors a certain interpretation, right? So this story from New York is the lead there is about a woman who walked into the police department and said, 2 days in a row, this guy on a bicycle groped me as he rode past. And they said, well, we don't have a name, we don't have an ID, there's really nothing we can do, sorry. Which may be true, however, they didn't count it in their crime statistics, right? So it turns out the police weren't reporting crimes that they had no way to follow up on. Which almost makes sense, right? If you're looking at the statistics in terms of cases, right? But you don't want to count cases; you want to count reports in this case. So you really have to ask where these numbers came from, and this is not unique to New York. I found 3 other cities where there were stories about bad crime data in the last couple of years. Also happened in LA and Milwaukee, I think. So one can only imagine that this is happening all across the country. And of course, there's an incentive, right? Because the cops want lower crime numbers. Here's another great example of problems with interpretation of data. You may have seen this. Twitter released these maps where they plotted all of the tweets from the last several years. A few percent of them have geolocation, right? They have the precise location from the GPS. And so here's New York according to Twitter. Now, I live in New York, so I have some idea when I looked at this what was wrong with it, and I had my suspicions. What's this map going to miss? What's not going to be on this map?
I don't yet understand what it is.
So what it is it's every time someone tweets when it's got a location, it makes a dot on the map. And it's a heat map, so the lighter blue areas are a greater density of tweets. and it's an accumulation over several years. And they're saying, wow, you can see, it's amazing. You can see all the highways, you can see the areas of higher population density, you can see the parks. That's Central Park up there. There's not a lot of people in there, as opposed to the apartment complexes next to it. This was presented by some people as, this is an amazing new way to make maps of the world. Well, no, it's an amazing new way to make maps of Twitter users.
Right. No, of course. Twitter users who are using smartphones.
And Twitter users have particular demographics. So take a look here. So New York is dense, right? So look at Brooklyn. This is, it's all filled in with dots. Each dot is 100 households, I think, right? In the Twitter map, Brooklyn's pretty sparse.
It's also bad service.
Yeah, that could be it as well. And the other thing you notice is there's this correlation. The densest parts of the Twitter map are also the richest parts of the city. So if you want the Twitter map to stand in for all people, it doesn't. It's going to be systematically off. So these are the sort of questions in data interpretation that you need to ask. Not only what's there, but what's not there. And there's come to be this phrase in data journalism, which is interview the data. And treat it with as much, what's the word? I guess respectful skepticism is maybe the way you would treat an interview subject. Because there's just so many reasons why it's not going to mean what you think it means. And some of them are innocuous. Data is always collected for a reason. That reason may not be the reason that you want to analyze the data. Or you may not even be collecting the right thing, right? So if you want to look at gun availability, well, how do you measure whether somebody has access to a firearm, right? You can count the number of gun shops. You can try to estimate the number of households that have guns in them. You can look at the fraction of suicides that are by firearm, which is actually thought to be the best possible indicator. But this sort of hazy concept, how easy is it to get a gun? There's lots of different ways you could measure that or try to measure that. And each way is going to give you a particular bias. So you have to think about that. What am I collecting? All of this is prelude, because I think this is relatively intuitive for journalists. We're used to asking these types of questions, and there's a few of them. Demographics doesn't normally come up when you're talking to an interview subject. But now we're going to get to statistical testing. And we're going to talk about these other problems that you might have in data interpretation. The main thing we're going to talk about is chance. How many of you have done basic probability or randomness? Like if I say probability distribution, how many of you does that mean something to? All right, good. So we know where we're starting from. Let's start with rolling a die. 6-sided die. The first question we're going to deal with is the pattern I'm seeing by chance? So let's take our example. So we look at our school grade data. We see that smaller classes have higher grades. We map cancer cases, and we see that they're higher near the oil refineries. We look at tax rates versus industry. There's all kinds of relationships we might want to look at when we're exploring this type of information. But there can be patterns by chance. And patterns by chance are a lot more common than most people would suspect. So I'm going to try to build up an idea of what chance looks like for you. And again, we're going to start with a die. And we're going to start with a fictitious story. You're a journalist. You're going into a casino. And your suspicion is that the die that is being used for, I don't know, craps is loaded, right? So it's weighted so that one of the die always has a 1 with much higher rate than you'd expect. So if I gave you a die and I handed it to you and I say, is this die loaded? Tell me. How would you find out?
By the number, if it's unusual, if the same number comes up more than the other numbers.
Right. So you roll it and you...
Over, 3 times it comes, 6 times, 4 times out of 6 is the same number. It's weird.
So you roll it 6 times and 4 of those times it's a particular number. Is that good evidence? Many more times. Okay, how many more? 100?
I mean, the more times you, I guess the more you do it,
Mm-hmm.
Probably look up the probability of like a 6-sided die online and see what the various probabilities are. And then once I'm at a point where I'm rolling and like really, overweighing probability of getting one number.
Yeah, so your intuitions are right. You want to do it a number of times. We're going to talk about how many more, and we're going to talk about what rolling a 6-sided die should look like. So if I roll a die 60 times, how many times should each number come up? 10 times. Let's try it. There's a chart that I made by rolling a die 60 times. In fact, we're going to start the interactive portion of the class here. Okay, don't freak out. This is a language called R. R is a free piece of software for statistical testing. And I'm going to roll a die 100 times and show you what it looks like. So first, there's this little... I'm writing a little function that just rolls a die. So if I just say die roll, it gives me a number. If I say do it 100 times, there we go. Gives me all these numbers. And then I'm going to make a little histogram of them. You know what a histogram is? It just counts, right? It just counts how many times each number appears. There we go. There's rolling a die 60 times. Does that look like you'd expect it to? So, all right. This one I only got 7 times. How about this one? Got a lot of 3s. Yeah. Is it a suspicious number of 3s? No? Not quite? How many 3s would you have to get before it was suspicious? What if it looked like that? Is that suspicious?
Yeah.
Why is that suspicious?
So, what is it, 17?
Yeah. So let's try this a few more times, though. I'm going to go to R again, if I can find it. I'm going to keep...
It's random.
It is random, exactly.
You know, so, I mean, yeah, sure. I mean, I guess statistically, you'd have 6 chances to get, but, I mean, randomly, who knows? I mean, it could be weighted to one number.
It's like, what are the odds of that could happen? Yeah.
Right. So what I'm going to do now is we're going to try to estimate what are the odds. I'm going to make a little function that plots many rolls as once, and I'm going to say many rolls of 60 die. Oh, God. What happened? There we go. We got debugging on the fly. All right, so here's 9 rolls. How many of them would you say have an unusually high, something that has an unusually high weight on one number? Maybe that one and that one?
Yeah.
So 2 out of 9? Let's do it again. How many of this one?
Isn't it sort of like blueberry in a muffin? Like some bites gonna have a lot, some don't have any at all.
Exactly. But the question I'm asking is, how often do you get a bite with a lot of blueberries? Right? That's an actual number there. Because the question I want to ask is, how often does chance look like a pattern? And so if I give you one of these histograms and I say, does this look suspicious to you? Either the die is actually loaded, or it happened randomly. And here's the central core of the argument we're making this morning, is that if you can prove that the pattern that you're seeing only happens very rarely by chance, that's evidence that it's a real pattern. That's the core idea of all of the things we're going to do today. So to prove that it's rare, the first thing you have to do is you have to have some idea of how often it actually happens by chance. So that's all we're doing here, is I'm just trying to calibrate your intuition of how often, if you roll 60 die, it's going to look like the dice is loaded. And I'm thinking it's, looks like 1 or 2 out of 9 here, right? So let's call it 10-ish%. So that means if you walk into a casino and they let you roll that die 60 times, and you get something that looks like this, and you're like, well, shit, this die's loaded. I got a story here about, a gambling scam. What's the chances that it's actually just random?
Really high.
Well, about 10%, right? Because we just said that if we're going to do this, right? How often? The question I'm asking is, how often does a random pattern look like something is actually there? And we can do it just by looking at it a lot and sort of counting. You with me so far? So a few other things. This is something that someone alluded to earlier. Now I'm going to roll 600 times. What's different? Yeah. So they're flattening out, right? Now they're looking more and more uniform. So now if I roll 600 times and I get something that looks like this, am I more suspicious or less suspicious? More suspicious. Okay. So this is a basic statistical idea, which is that you used the word error. The statistics term is variance. It's how much. I mean, it has a technical definition, but the intuitive definition is what is the spread of numbers that I'm going to get when I try multiple times. I actually have here a loaded die, and so let's play with the loaded die a little bit.
Can I ask a question?
Yeah.
How do you figure out how many times? We jumped here from 60 to 600.
Mm-hmm.
We could go to 6,000, 6 million. How do you know? How do you try to figure out how many times you have to go before you can get an answer? I mean, maybe 6 million is unnecessary.
Yeah.
You can get an answer before that. So how do you know what that one is?
So the short answer is there's formulas. You can work it out. The longer answer is that in your case, normally as a journalist, you won't be generating the data. You've got data as given, and you have to figure out whether you have enough of it to draw a conclusion. I'm going to play a little bit with a loaded die, and I'm not going to tell you how loaded it is, although you can actually read it right off the screen there if you were looking closely. So I'm telling you this is a loaded die. Tell me which number you think is loaded. I'll just show you a lot of these. Does anyone have a guess? Number 2. Someone said 4. What's really going on here is we were not rolling it enough to know. But now I'm going to roll it 600 times. Anyone got a guess now? Number 1. Now I'm going to roll it 60,000 times. So we should get 10,000 rolls for each die. Yeah. So there's 2 different concepts here. One is how much it's loaded by, right? So a little bit excess there. In fact, what I've done, if you look at the code, is I've said it's going to land on 1 18% of the time. If it's a six-sided die, it should land on one about 100 over 6, which is about 12% of the time. Or my math right there? No, 16. So it's just a few percent over. And the smaller the difference you're looking for, the more data you need to find it. So I've now tried to demonstrate to you the very first thing you need to know, which is more data gives you more certainty that what you're seeing is really there, and the smaller the effect you're looking for, the more data you're going to need to find it. If the effect is huge, right? So say you plot your oil refinery data, and census blocks within a mile of the oil refinery have 10 times the cancer rate of ones that aren't. If you're starting to look at that level of significance, you know, something that's that big an effect, you don't need very much data, right? Maybe, you know, if you have 10 cases of cancer instead of 1. But if you have, you know, 3 cases of cancer instead of 2, right, exactly. So which types of cancer are going to be hardest to link to the oil refineries? No. Oh yeah, so the time lag is a really important thing too. But statistically, is it going to be the rare cancers or the common cancers that are going to be hardest to? Now the common cancers are going to be easier because you have more rolls of that die. Does that make sense? It's the rare ones, right? If I'm looking at a difference between 10 cases and 100 cases, that's pretty good evidence. And we'll get to just how to tell if it's good enough soon. If I'm looking at 3 cases versus 2 cases, if I, again, think about rolling that die, how often am I going to get 3 versus 2? So the rarer the events you're looking for, the more data you're going to need to reach statistical significance. Just like our loaded die example.
Sorry, if a rare cancer,
Mm-hmm.
then the fact that you have, you know, even if we're talking about 10, but if they're really rare cancer, the incidence, you know, what are the chances that they have exactly the same place? I mean, that also shouldn't that be also considered? If they're rare, they don't, huh? No, but I mean, you don't. But if they, you know, even if they're rare cancer, if you have a small, even small concentration, but you know, generally would be 1, and then suddenly you have 10 in the same place, which is near a refinery. Wouldn't that be an indicator that there's something wrong?
Well, the problem with rare events is that very commonly it will look like there's something wrong when there's not. So again, I'm going to go back to our, again, let's look at our die roll for a second. Let's say that the number 1 corresponds to that. Let's say we're looking at the number of cases of a rare cancer in different counties, and number 1 is the county that the refinery is in. If I only have 10 cases overall, how often am I going to see, just by chance, let's say that the cancer rate has nothing to do with the oil refinery. Let's say it has to do with diet. How often am I going to find, just by chance, that there's a lot of cases in the county with the refinery? Right? There's only 10 cases in the whole state. So there's one, right? That looks like there's the highest number of cases in the refinery. Let's take this one, right? Look at that. If you get that data, you're like, whoa, there's 6 cases next to the oil refinery and no more than 1 anywhere else. The problem is, about half of these graphs show that kind of pattern. So the rarer it is, the harder it is to separate chance from effect. That's the problem. Does that make sense? Whereas if I start to roll 100 times, then the graphs start to even out. So if I get that big spike when I have a cancer there's 100 cases in the state instead of 10, it's much better evidence. And we'll get into how much better evidence in a minute. Okay. What if I want to look at 2 dice? If I roll 2 dice and I look at the numbers that I can get, what should that look like? Anyone a gambler here? Gambling will help you a lot in stats. No, seriously. That's where the subject started. Probability theory started in the 1600s with games of chance. And the fundamental intuitions all come from these types of gambling ideas. So to figure out what it should look like, I'm going to take these 2 die and I'm going to count all of the different ways they can land. The first die can be any number 1 to 6. The second die can be any number 1 to 6. And then I'm going to take their sum. And in the middle here are all the different ways that can sum to 7. And so when I roll these 2 dice, I should get a pattern that looks like that. What do you think I'm actually going to see when I roll the die? Is it going to look like this shape? No. It looks like that. Here's, I think that's 100 rolls again. Sometimes I get that shape. Sometimes I don't. And again, the more rolls I make, the closer it's going to get. So I'm actually going to do this for you really, really fast.
Could I ask a question?
Please.
I'm not ever going to do data myself. I'm going to be interpreting data that other people do.
Uh-huh.
I can't imagine a scenario that I'm going to have time to do my own data like this.
Mm-hmm.
So are you? I mean, I'm just. Is this a way for us to learn, or for me to learn how to better interpret data that I do get, and whether it's statistically significant or whether it's just somebody who doesn't have an idea, has a preconceived notion of what they want to achieve, and that's what they're showing me versus some significant, some real data? Is that the idea?
I want you to come out of this with an intuition about what statistical testing is.
Okay.
I want you to understand the logic of it.
Okay.
That's what I'm getting at.
Okay.
Which is why I'm sitting here showing you die rolls, because to understand the logic of statistical testing, you have to understand the logic of chance. Because statistical testing, how it works is you compute the probability that what you're seeing happened randomly.
Mm-hmm.
If that is low, you say, well, I don't think this is chance. And so I want you to be able to read a scientific paper or look at data, and I want you to say, be able to look at it and say, 20 cases, that's not very much.
I see.
How often is 20 cases going to look like that by chance?
I see.
And, if you have 20 cases of something, and you're saying all of them occur, next to the refinery, for example,
Mm-hmm.
that's going to happen like 30% of the time, right?
So it's a way to be better at interpreting the data.
Exactly. And I'm going to...
Skeptical.
Exactly.
Like the die roll guys, they're getting a probability of the numbers and betting with the probability and figuring out, well, I'm going to win a certain percentage. Is that what they're...
Right, but only if they do it a large number of times.
Yeah.
Right? And the number of... So we all know, we all have this intuitive sense. It's actually called the law of large numbers. And it was worked out originally in the 1600s by Bernoulli. And it says that if I roll the die, but roll the die stands in for something happens with an element of chance. Many times, over time, it's going to average out to some pattern. And we can calculate what that pattern should look like because we can do this, right? We can do this theoretical analysis of what it should look like. But it doesn't look like that until you get a very large number. And what I'm trying to give you a feel for is how big. All right, so that's 100 of them, and we've still got all these funny shapes. If we get 10,000, that looks like what we would expect theoretically. Is that at all helpful?
Yep.
Okay.
Yep.
So, and
Thank you.
and I'm actually going to show you a very simple statistical test that you can actually do as well. Or maybe you can ask your friendly newsroom coder to do. Let's ask actually that. How many of you work in an organization where you have a journalist on staff with a little bit of a coding skill who can help you with this analysis? All right, so about half. That's good. The public talk is going to be about what that job is and why that intersection is interesting. So we looked at that. Who's heard the phrase null hypothesis? We got one. Okay. So if you're doing any kind of science, you're going to come up with a hypothesis and you're going to test it. In statistical testing, what we're trying to do is we're trying to choose between multiple hypotheses. And we have at least two. One is what we see happened by chance. There is no link between class size and school grades. One is what we see didn't happen by chance. Smaller class sizes cause higher grades. The "it happened by chance" is called the null hypothesis. Usually in scientific writing, you'll see that as H0. And we've been plotting this little graph, like what the die roll looks like when you roll two die together. That's called a distribution, a probability distribution, right? That is, if I do this many times, what is it going to look like? But many means like 10,000, and you don't usually have 10,000 different classes with different teachers, right? You have every school in the city, and maybe that's only 30 schools. And so, although there's this theoretical distribution, what you're actually going to see is something much more patternful. And so the question you have to ask yourself is, which hypothesis is true, the null hypothesis or the alternate one where I do think class size is there? And so you'll see this terminology. This is the basic language of statistical tests. So let's talk about this. You get the class scores, and you get the class sizes, and you're like, wow, the average is 10% higher in classes with 10 students. So is that evidence that smaller classes give better results? Well, maybe, right?
Yeah.
It depends. The question we have to answer is, how often am I going to see that result by chance?
Years. Yeah. You have to do more years then.
More years would help, although then maybe you have a problem where different things are happening in different years, right?
Yeah.
You might not always be able to just go and get more data. You have the data that you have. And so the question is, do you have enough to draw a conclusion? Or, in the language of statistical testing, to reject the null hypothesis. Has anyone heard that phrase before? You're going to see that in papers a lot. That doesn't mean it's true that smaller classes give better grades. It means it's unlikely that we would see this by chance. That's what that actually means. So to do that, we have to know what this null distribution looks like. So remember, we made this little chart here, or just for rolling a die, we just expect it to be flat. What do we expect the distribution of class sizes? So suppose there's no difference in teaching between large and small classes, or no difference in the students' learning between large and small classes. What distribution do we expect for their grades? Yes?
Then the grades would be equal regardless of, like, if class size, if you plotted it, it would be flat, right?
Right, but not everybody's going to get a 78.
Right.
Right, different people are going to get different grades.
Yeah.
But we don't. So we
I mean,
don't.
like the average, I guess, like the average class score per class.
Right, so you would expect that the if you plot class size versus the grade, it would be flat. Yeah. So here's where statistics textbooks normally go off into some sort of bell curve, like normal distributions and like modeling distributions, but there's actually a much simpler way. And I'm going to give you a very simple technique to answer these types of questions, which is that, let's talk about two classes for a second. If the student's learning is really the same between the two, I can just switch them. Right? If all of the students are actually having the same experience, then it's just chance that these students ended up in this class and these students end up in this class. So if I want to ask how often, given that I have this set of students, how often are the good half going to end up in class A, which is smaller? All I can do is I can rearrange them in all possible ways and look at the average class score over all of those rearrangements. So here's what I mean, like in real practical terms, right? So say these are scores on a standardized test. I guess I'm imagining that 1.0 is the average on your standardized test. And this is what I see. I see class A has all of these numbers, and I'm actually going to compute a, here we go. If I look at these two sets of numbers, and I type them in, and all I've done is I've asked for the averages, 1.1 versus 0.97. So class A has higher scores. And they're not even the same size in this case. One class is smaller than the other. All I've done under permuted data is I've just switched them up. And if I switch them up, then they're going to have some different average. And maybe class B is going to have the higher scores. I think in this case, it looks like class B has the higher scores. It's got 1.46, 1.38. And I can switch them up all of the possible ways that they can be switched up. There's a few thousand different ways that this might have happened, right? So what I'm doing is I'm reconstructing chance here. I'm assuming all the students are the same, and I'm asking, let's just look at all the different ways that could have happened. It's just like counting the die rolls here, right? So I asked here, what are all the different ways that I could have landed with 2 die? Here I'm asking, what are all the different ways I could have switched the students between the classes? And I'm actually going to draw it. Oh yeah. So here's sort of what's going on here, right? This is the scores on one class, this is the scores on the other class. And it looks like the scores in the red class are kind of higher, but what are the odds that that happened by chance? And to answer that question, I'm going to scramble them all the different ways they can be scrambled and plot a histogram of the outcomes. So what I've plotted here is I've taken the average of one class minus the average of another class. And normally the average is, the difference is somewhere around 0.1. Sometimes it's as high as 0.4. The biggest difference I can get is like if I take all of the top scores and I put them in one class, and I take all of the bad scores and I put them in the other. But mostly I get a difference somewhere here. This blue line is the difference that we actually saw between the two classes. Does anyone want to guess? Like, okay, now I've shown you this fancy plot. Why have I plotted this way? What does it mean to look at it this way?
Doesn't it show that the actual result isn't the most likely thing to happen by chance, right?
Yeah, it isn't the most likely.
But it's not the least. I guess it's maybe it's in the middle somewhere.
So the question we want to ask is, how often am I going to see a difference between the two classes that's at least as big as what I saw? And the answer is, well, all of these cases here, everything to the right of the blue line, that tells me how often I'm going to get the scores looking much better in one class than the other class just by chance. And this is like, what, a third of all of the cases here? So you're looking at the area, right? Because each of these counts one possible outcome. So you're thinking of the area under these bars versus the area of these bars. So that means yeah.
Does this mean that if you mix the kids, so you've got the teacher, the class with 10 kids, and then you got a bigger class with more kids, and the kids with the bigger class got the lower scores, and if you mix them up, it looks like is that if you were a kid who was in class B and you were all of a sudden in class A in the smaller class statistically, that I could be totally wrong. It looks to me like the kids in class B are still not performing at the same level as those in class A. Despite the fact that they've been switched, but I could be.
So we're doing a sort of thought experiment here. We're saying,
okay,
how often, if all of the students actually have the same experience and it doesn't matter what class they're in, how often, if I take a set of students with these grades, how often am I going to see that the smaller class has better grades just by chance? And so I'm counting, it's exactly the same logic as counting the number of ways that I can roll the die. What I'm doing is I'm listing out every possible way that I can split the students between these two classes. So, this person could be in this class or they could be in this class, and then that person can be this class or this class, and this person can be in this class or this class. And I'm saying for each of those, I'm asking, what's the difference in the average grade?
You're saying that like about half the time you won't see that difference, like mix them up. About a quarter of the time you see some difference, and maybe a quarter of the time you see it.
Exactly, yeah. So most of the time I see a difference around 0.1 between these two classes. Sometimes I see a difference as big as 0.4. And that's very unlikely, right? So look at this, 700 cases up here, and here it's like 10 or something. And there's thousands of cases overall, right? The total number of cases, I got 10,000 different here, right? So
I was just thinking, like, because you put that blue bar, and visualizing like another blue bar a little to the right of the 0.2, because that could be another group. Yeah.
But this is what we actually saw. That blue bar is the scores we actually got, right? So when I look at this, what it tells me is that, half the time, a third of the time, all of those cases to the right of that bar, I'm going to see just by chance something at least this good. So if I might have seen a difference between the two classes by chance 30% of the time, is that evidence that smaller classes have better teaching? It's very weak.
Yeah.
Yeah. What you're looking for generally, let's ask in science, what's normally the threshold for the possibility of a chance result? Does anyone know? So that leads to the question, right? How sure do we need to be, right? So we know that as this bar goes to the right, there's going to be it's going to be less and less likely that what we see happened by chance, right? So like the bite of the muffin example, right? Where as the number of blueberries you got in one bite gets bigger, it's less and less likely that you closed your eyes and took a bite, as opposed to like picking the muffin with the most blueberries and taking the bite with the biggest bite, right? So this is a way to calculate what are the odds. This is the fundamental question you should be asking. What are the odds this happened by chance? How low does that number need to get? There's actually a a generally accepted answer. Oh, no, that's not quite where we want to go. So you've seen p-values in papers in statistical testing. What the p-value is the calculated probability that the result they saw happened by chance. And normally you see p smaller than 0.05, which means a 5% chance. That's generally considered publishable. It's also arbitrary. Why not 1%? Why not 10%? You sort of had to pick a standard. What's that?
What was the paper you just said?
5% chance, so 0.05. But
I'm sorry, just so I'm clear. That means there's only a 5% chance that it happened by chance.
exactly, yeah.
So it's 95% likely to be causal.
It's 95% likely to be non-chance,
Okay.
right? You still may be misunderstanding something,
Yeah.
but the first thing you want to rule out is chance.
Right.
Now, just like our loaded die example, if we have a lot of data, we can detect very small loadings on the die. So there's two different concepts here. This p-value thing, what's the likelihood it happened by chance, that's called significance. And so you're going to see things in science papers, significant to p smaller than 0.05. What does significant to p smaller than 0.05 mean? Does anyone want to translate that into English? It means 5% chance that it happened randomly. Right? So 5% chance that what you're seeing is just luck. I'm going to go to my favorite teaching tool, XKCD, which is a geeky webcomic. They have a beautiful example of this. So, two scientists trying to figure out, did jelly beans cause acne? No. We found no link between jelly beans and acne. P, that should actually be smaller than 0.05, right? So they did the experiment. The answer is no. But then somebody says, oh, but it's a particular color that causes acne. And so they test all the colors. Purple jelly beans, no. Brown jelly beans, no. Red jelly beans, no. But then they try it, if you count, there's 20 of these. Green jelly beans, 95% confidence, only 5% chance of coincidence. That's what it means. So if all of the p-value calculations that you see in science are working correctly, 1 out of 20 scientific results should be wrong. Is that a high or a low number? I don't know, right? Should we say that only something with 1% chance of being wrong is publishable? Well, then we'd get a lot less science done. We'd throw away a lot of things that are true that we just don't have enough data to prove. In fact, we suspect that it's greater than 5% of results that are wrong. There's a bunch of work looking at replicating studies and various statistical properties. We actually think it's a lot higher than 5%. But nominally, what the discipline has been aiming for with these types of statistical tests is a 5% chance of error. And so that's why we're all asking these questions. Now, but there's two numbers here, right? One is significance. There's this other number, which is effect size. And so you're going to see something like this. Class grades differed by 3%, p smaller than 0.05. This tells you what the likelihood that it's just random is. That tells you how big the difference is. There's different numbers, right? You can have a very large effect and a small significance, right? So we see a huge difference, but we think it's quite likely it's due to chance. So that was what we saw with this loaded die, right? Big effect, small significance because, well, we know from our tests that you're going to see this about 10% of the time. Or you can have a tiny difference but be really sure, which is what we saw here. So whenever you're doing, yeah? Okay. Yeah, we're going to have to cut a few things. So whenever you're doing statistical testing, you end up with two numbers. And what you really want for your story is a big difference in high significance. So first of all, something with really low significance, right? So if there's a 30 or 40% chance that this is just random, can you use it? No, you can't use it. If there's only a 1% chance that this is random, you can use it, but maybe it's a difference it doesn't care about, right? Maybe we know that eating broccoli reduces cancer rates, but it reduces the risk by, 5% over everyone else. And we're sure, because we have lots of data. But we also don't care because it's just not a very big change. So what you're looking for is big effect size, high significance. Make sense? Don't confuse the two, right? So just because we're really sure doesn't mean it's important. It just means we're sure. But we might be really sure that it's a very small difference, which is good science, but not necessarily interesting. Right? So you've all heard about negative results in science, right? Negative results are important. It's important to know that eating broccoli won't help your cancer risk. And you want to be sure about whether it does or not. But probably not interesting science journalism. Unless, of course, everybody thought that it did, in which case it is. So there's two numbers. So here's a basic question when you look at data analysis. I see a trend. Is it real? Normally, how you look for trends is you look at a scatter plot. So this is a story that I actually worked on because of all the gun violence stuff recently. Trying to look at, do more firearms correlate with more firearm homicides? So I took all of the data for all these different countries. This is just developed countries. Because actually, developed in different parts of the world this pattern looks different. So right away, I had to make choices about what subset of the data I used, which you should all be suspicious of. Anytime you hear somebody excluded something from analysis, you should ask why. You should ask if it would change the result. So this is this earlier step of interview the data. But let's say for the moment that comparing just developed countries to developed countries is justified. All right, so firearms per 100 people, homicides per 10,000. What do you see? Tell me just in words, what do you see when you look at this graph? So here's the U.S.
A lot of firearms, not a lot of
Very, very rare correlation
Well,
for one country.
for one country, you see this one country, which is
Right.
the U.S., which is huge number of firearms and a huge number of firearm homicides. Okay, so
Where is that second country?
where? Here? That's Chile. That's Switzerland. That's Finland. Switzerland has a lot of guns because they have a militia. They don't have an army. But, they have half the number of guns, but only a quarter of the number of homicides. So do you think there's a pattern here? What about the rest of the world, right? The U.S. is here, but maybe it's weird in some way. If I take the U.S. out, is there still a pattern? Not really, yeah. So how would I do a statistical test? How would I get an idea of whether this relationship is random or not? Anyone got an idea?
Isn't the idea that you would, if for a given number of firearms, how likely are you to see X homicides, and how likely is it to like chance that you would get a lot of homicides with a certain number of firearms?
Well, what I'm looking for is I want the chance that if there's no relationship at all, if the number of homicides is just a roll of a die, what's the chance that I'm going to see this pattern by chance?
Yes.
Sorry, you had a question?
I was wondering if does this include the death by firearms illegally acquired? Is that
Yeah, all
do
cases.
you make the difference in this?
This data, no, it's just death by firearms, full stop.
This is not annual or.
It's annual. It's annual rates. It's 2011 data, I think. And it's population adjusted on both axes.
Well, can you compare that with countries that used to that regulated? Well, I mean, how do I say this? Can you make a comparison within the same country that used to have, would allow civilians to have guns and then
Yes.
change the law and
Yeah.
then see a pattern there where there's a difference?
Yeah, but then you have to ask the question, how likely am I to see that pattern by chance? And and also what other factors, right? So if there's all of these other things that are going to change the level of gun homicides, how do I know that what I'm looking at is because the regulation changed and not because of something else? We're going to get into cause in a second. So here's the trend equivalent of the charts I showed you of rolling the die. What I've done is I've drawn 5 random points, and then I've drawn a line through them, right? So just 1, 2, 3, 4, 5, and then I've chosen a random value, and I've drawn a line through it. How many of these charts would you say look like there's a solid trend? Yeah, lowest right looks like there's really a trend going on here. Or maybe this one, right? So maybe this isn't a line. Maybe this is, imagine these are car crashes at an intersection. Oh, they went up for a while and now they're going down. The city council's really done a great job. All right? So you really want to write that story. But what I'm trying to tell you is if you only have 5 points, these are all random, right? So I'm going to say about 2 in 9.
Can you get more data going back years?
Yeah, sure, if you have it.
How the ones that you had before, how far back you went?
For what? Which one?
The graphic that you did before?
This one?
This one, yes.
1 year.
Just 1 year.
1 year. So can you do it for the last 10 years?
Sure, although something may have changed over the 10 years. So, but I'm looking at a different variable, right? I'm imagining that each of these is 1 year now. Like I'm counting the number of car crashes on the corner. And so I plot them and I see that there's a steady downward trend. But what is the chance that I'm going to see a steady downward trend just by chance? Somebody actually give me a number. From this chart, you should be able to give me a ballpark number. How often am I going to see a steady upward or downward trend just randomly if I take 5 numbers?
Oh, like 2 out of 9.
2 out of 9. So what is that in terms of percentage? Yeah, 23, 20 odd, right? Something over 20. All right, so is that, if you see a trend with only 5 numbers, is that statistically significant?
No.
No.
Because this is like the p-value, right?
Exactly.
Yeah.
So if you're going to see it look like that 1 out of 5 times, it's not really a story.
The p-value is too high.
Exactly.
Yeah.
The chance that it's going to look like that just randomly is much too high. Now for firearms, I don't know what it theoretically should look like, but I've got this trick, which is if there's really no relation between the number of guns and the number of murders, then if I swap the number of murders, just switch them around between the data, right? So I take Chile's number and I give it to Argentina, and I take Germany and I reassign it to Canada. It shouldn't make any difference. I should see the same pattern. So that's what I've done. This is the same idea, but now I've just scrambled all of the country labels. So which one of these is the real data? In fact, we can do this experiment right now. So here you go. One of these is actual data on gun deaths versus firearm ownership. And the rest I've made by scrambling the numbers, right? So I've reassigned the countries randomly. Which one is real? Can anyone tell? Anyone want to guess? This one?
Yeah.
So that's number 5, counting from the top left. Anyone else got a guess?
I'm a bit lost. I don't understand this this way of scrambling data. Why are we going to get something to? I don't understand this.
Why we scramble it?
Yeah, it seems easier when you're explaining to the kids in school. I don't
so
get it.
What we're trying to do is we're trying to say, okay, suppose there's no relationship between the number of gun deaths and the number of guns. Well, then we should see the same pattern. The plot should look the same if we switch all of the numbers between countries. Right? So if there's a very clear relation, like say there was a very clear upward trend. So here, I've actually got a picture of this. This is a course I taught in Hong Kong. I actually gave this as an assignment. All right, so here's an example where, okay, which one is the real data and which ones are the scrambled ones? Anyone want to guess which one is the real data from that?
The top center.
Yeah.
Yeah.
So perfect correlation here, right? So there's this very clear pattern. If I take it and I scramble which number goes to which country, it's easy to tell that it's scrambled. So like you never get that straight line by chance. And so that means there's a very low probability that that straight line happened randomly, which means it's very strong evidence. But here, with the real data, one of them's scrambled. Or sorry, actually, here we go, that's our experiment. One of them is scrambled.
They're not that different.
They're not that different, exactly. Which means...
But it seems that the US is still up there, regardless of
Mm-hmm.
how you scramble the data.
The U.S. is still up there. So we can definitely say that the U.S. is an outlier. It's different from all the other countries. But that's different than saying there's a trend. Because all of these look the same, like if you can't even tell the real data from the randomly scrambled data, that's very strong evidence that there's no trend.
Because the real data that you look at, the real data, it's likely that, I mean, it looks so similar to the data that was just produced randomly.
Mm-hmm.
You know? Yeah, that's, yeah. Okay.
Exactly.
So you just showed that there's no connection between increased firearms and
Exactly.
Exactly.
Yeah.
At least in this data.
Yeah.
Or that there's some other thing that would not, that goes into this Like there's some other variable.
Well, there's many variables.
Yeah, right,
Yeah.
exactly. So, but just with these two variables.
But
you can't
these
do
two
that.
variables aren't it.
Right.
Right.
Yeah.
Yeah.
Right, but I mean, homicide has many variables,
Mhm.
right? It cannot be only whether you have a gun in your hand or not, or in your drawer or not.
Right.
I mean, it's linked to a lot of many variables, but even and therefore, because countries have very different variables, it's really difficult to get a partner. Apparently, it's impossible to get a partner. But isn't valuable the fact that there is such a huge difference anyway between one country and all the others? Isn't that the data that should say something?
So it may be, so here's the story you can write. The US has both way more guns and way more gun violence than any other country. But there's no evidence that a larger number of guns is the cause of more violence
Necessarily.
internationally.
Yeah.
It might be the cause in the US. It's not a cause internationally because there's no pattern. Right? It's not a pattern, it's an outlier. Does that make sense? So you have to be very careful to avoid misleading your readers. You can say the US has the highest number of guns and the highest rate of gun violence, but that's not a trend. It's one point.
Well, but because you don't kill a person just because you have a gun, so obviously there is something else in play.
Mm-hmm.
But given the huge difference,
Mm-hmm.
Doesn't that show that if you have a higher number of guns, you will have a higher number of homicides?
No.
No.
Absolutely not. Because we can't tell the real data from the fake data. So you're saying...
But there is one thing that doesn't change, even when you change the data, which is the fact that everybody else is so this big distance. I mean, how do we read that?
But the U.S. is only 1 point though, so there's not a trend. I think is what he's
Yeah,
saying.
and furthermore, you don't even know cause, right? Maybe people buy more guns because they're living in a dangerous place, right? So we have two problems. We have to show that the pattern is not due to chance, which is everything we've done so far, and we have to show that causality runs the way we think it does. And I'm actually going to jump ahead to talk about causality because we're almost out of time. We're going to skip all of that. Have I really found the cause? So far we've talked about correlations. You've all heard correlation, causation. You've all heard correlation is not causation, right? So this is going back to our class example, right? So say we've done the statistical test. We're like, you know what? Seeing this much of a difference between the two class scores only happens 3% of the time. This is statistically significant. This is a real effect. This class is doing better for reals. Not by chance, we think. But is it really doing better because of why we think it is? The problem is that we will make up stories. So look, as the number of Facebook users goes up, the Greek debt crisis gets worse. As the these are correlations. As the NSF budget goes up, the average temperature rises. Right? So this is silly, but
Yeah.
just because you have a pattern doesn't mean that you have cause. It's just a pattern. So correlation is not causation. So when you see a pattern, there's only a small number of ways that pattern can occur. This is the one we want. Smaller class size causes better scores. Now, better scores cause small class size. That doesn't really make sense. But think about the gun example. A greater number of homicides causes more people to own guns. That's actually plausible. Maybe people are buying guns because they're scared. And you believe it's the one on the left, but you have to rule out all of these other cases. There you go. So that's what we want. If you have a gun, you're going to use it. Here's the other direction. If it's a dangerous neighborhood, you'll buy a gun. Here's another possibility. Perfectly random, right? So this bottom one, is what we're ruling out with statistical testing. Right? We're ruling out that the relationship is due to chance. Well, we're not ruling it out, but we are putting a bound on the probability. We're saying there's no more than a 5% chance or a 10% chance or whatever percent chance that this is random. That's everything we've done so far is to put that bound. But now we have these other possibilities that we have to rule out as well. Does anyone read the OK Trends blog while that was running? It was the data scientist from OkCupid talking about how to make OkCupid work. And one of the things they did is they looked at the response rate versus the words. So if you put the word sexy in your first message, you're going to get 25% or, yeah, exactly. Whereas if you put the word awesome, it's much higher. So it's very tempting to make a little causal story, right? If you put the word cutie in your first message, this is men writing to women. The woman's she's not gonna write back. That's the story that you want to tell. But could be all of these other cases. Now, obviously you write the message first, so the backwards causality can't happen. She didn't, her not writing back doesn't make you put the word cutie in it because one happens. So if there's a temporal order, you can rule out causes sometimes. But what's actually going on in this case is this other thing. There's something else. Or these two are the same, except sometimes you can see what it is and sometimes you can't. So in this case, we're looking for a variable that causes both her not to write back and a guy to use the word hot. So what's the variable that causes both of these things?
Maybe hot people are being besieged by lots of notes.
So we look at the data and we think it's this, but what it actually is this, right? So this is called a confounding variable. So just because you have a pattern and you've proved the pattern isn't by chance, the next step is you have to, you're gonna want to tell little stories about cause, but you got to make sure you understand the structure of the causes. And luckily, there's only 5 cases. That's it. So you have to figure out which of these it is. And that means you have to find evidence that it's not these other things.
But doesn't that change? I mean, there could be many other reasons besides the 2 reasons you put down there for why she's not responding. I mean, so, I mean, there are a lot more variables than...
There's tons of variables, but you're asking the question, why do I get this relationship? So I've got 2 variables, response rate and whether or not I use the word beautiful.
Yep.
And I know there's a pattern. Why? And there's really only a few possible cases. These are all of them. And what you think is telling a woman she's beautiful doesn't work, but what's actually happening is because she's beautiful, that causes both a lower response and someone to use the word beautiful. So you got to work out which structure it is, and normally the way you figure it out is by ruling out the ones that it can't possibly be. Anyway, we are at time. In fact, they've even stopped filming. So there's one more idea which we're not even going to get into. Yeah, they took away the camera. We're that much running over. Which is generalizability, right? So this is the idea. Just because you know that a smaller... Say you've done all this work. You've seen a relationship between class size and grades. You've shown that the relationship is very unlikely to happen by chance. You've shown that the causality runs the way that you think it runs, which is actually very hard to do. You've proved that it's not because better... So for the class size example, right? Maybe it's better funded schools have better trained teachers and smaller class sizes. And so the fact that you see a small class size correlating with higher grades doesn't mean that they're getting higher grades because it's a smaller class size. It's just that the better funded schools also pay better teachers, right? So you've got sort of 3 steps here. First, you have to prove that the pattern doesn't happen by chance. Then you have to prove that the cause is the way you think it is. And then you have to ask yourself, am I going to talk about these schools or am I going to try to make a point about everything? Because if you're writing a story saying, in Rhode Island, smaller classes cause higher grades, are you implying that it's going to work in Texas as well? And so you have to think about the generalizability of your results. And that's this whole other tricky area. And statistics can help with that too, but we're not going to talk about it today. Generalizability comes in a lot of different forms. If I interview 3 people, do they really stand in for this whole group of people? If you start to think, well, this is common sense, common knowledge, everyone believes this. Really? Because the people that you know are going to be a certain type of person. People grouped together with people like them. Margin of error of a poll, same thing. I asked 500 people. This is where statistics comes in again. Is that really representative? That's the margin of error of a poll addresses this problem of generalizability. It gives you a chance that the error is, that it doesn't generalize, right? But we're not going to talk about that today. Anyway, so this is the short version of how to know if what you're looking at is really there. The first thing you have to do is be skeptical about where the data come from. Then you have to establish if the pattern is there by chance or not. And then, even if you do have chance, very often what you really want is a cause. A cause is a whole other problem. And then, are you going to imply, or will the reader assume, that these results hold in other places? And if you actually don't know, in Rhode Island, putting students in smaller classes improves grades. We don't know if this will work in California because XYZ. So you have to think about all of the implied generalizations. There may be something completely different. And we see this all the time, right? Policy in environmental policy in one country is going to be different from environmental policy in another. So just because carbon markets worked in Europe doesn't mean they'll work in China, necessarily. Now maybe they will, but the point is you have to make an argument for each of these steps. If you miss any one of these, it's very likely you're going to end up with stories that just aren't true. What's that? It happens all the time.
But I mean, how can we apply these, in practical terms? Our situation would be, we get data, we can get more data, but we don't, as you say, produce data unless we have a way to do the kind of things that you showed us. So how can we actually, put into practice what you're telling us?
Well, so the shortest answer is you can say no. Right? So someone comes to your editor, says, I've looked at this chart of gun violence. Where is it? And man, look at that. Clearly, look at the US is way up there, and then there's like this trend, and it's your job. What's that?
You can use like the line of best fit.
Right. So you can put a line of best fit, and yeah, it goes up. But the thing is, how often,
Right. But then
Yeah.
I should be able to do something like this, which I'm not.
Right. So the
Because we use data, I mean, you cannot not use data.
Uh-huh.
You have to interpret data, that's the
Right.
reality.
Mhm.
And I personally don't know how to use the software that we just showed, which is very useful, but it's a
Mhm.
little bit, So how can I, now
can
that I
you-
know where the problems are, how can I put it into a positive way and say, I still have to use data, how can I be reliable?
So I think your job as a reporter is to ask these questions and make sure they have good answers. And maybe you can't do the statistical testing yourself, but somebody needs to have done it. So that's either the scientist who wrote the paper, the think tank who's making the claim, or if there's someone in your newsroom who can do the test, they can do it, or you find a statistics professor. A friend of mine calls this consult your rabbi. Right? When you have a question about the statistical validity, you need to find a rabbi. You need to find an expert who understands the problem and can help you with it. But even if you're not doing the tests yourself, you need to ask these questions. These are the places where you need to be suspicious as a journalist. And Maybe that means, sorry, we just got to kill the story. Maybe it means the story has a different headline. Maybe it means you find more data.
Well, I think any journalist is going to be skeptical of data that they receive. They're decent. They go to a number of different people and say, does this ring true to you? Does this seem possible? Does this seem probable? You know.
But there is a lot of assumption, and especially when someone comes out with something, there are 50 other media who report the same. So, and if you look at the data, sometimes you just need one interview with an expert to say, nobody's looking at this variable.
Right.
You know?
But ask these questions, right? Exactly. When someone says, I see this pattern, did it occur by chance? And does the cause work the way I think it does, right? So yes, asking experts is good, but you know, how you tell if the expert's giving you good answers, they have to be able to answer these questions. How did I collect this data? What's the odds that I'm going to see this pattern by chance? And I don't mean like, what are the odds? This is not a rhetorical question. What are the odds is not a rhetorical question. What are the odds is a question that should have a number as an answer. Okay? Anytime someone comes up to you and makes an argument about this couldn't have possibly be a coincidence, say, oh yeah, what's the number? And even if you can't calculate it precisely, estimate it. Is it a 50% chance? Is it a 10% chance? And generally in science, a less than 5% chance is what you're looking for. And then there's this causality problem. All right? These charts seem hilarious, but when I show you the gun violence chart, it doesn't seem hilarious. Just because it seems like it makes sense doesn't mean it's true. So you got to figure out, even when the pattern is real and not a coincidence, you got to figure out which one of these cases you're in. Luckily, there's not very many. You got to rule them out.
And that doesn't even put the political layer on top of it all. I mean, I'm looking at your gun violence things, which, you know, could be interpreted by one, you know, a policymaker to say X and another policymaker to say Y. Could. So you got to, you know.
But only one is right, though.
Oh, I know that.
Right.
I understand that. Yeah. Yeah, no, I get it. Yeah.
What? I'm curious to know what you think of the story that comes out every single year, which is gun violence so far is, or homicide rate is down this year compared to last year, or homicide rate is currently up this year compared to last year.
Right.
It happens every city, every big city.
So that's fine. I mean, that's a worthwhile thing to report. Where you can get into trouble is gun violence is down this year because. And with 1 year of data, you can almost never say why. But a really good question to ask is, what's the natural variability, right? It's that, you know, if gun violence has been between 90 and 100 for the last 10 years and now it's 200, that's interesting because that doesn't happen, that's not likely to happen by chance, right? But if gun violence was 98 last year and it's 92 this year and it's been between 90 and 100 for the last 10 years, I don't know. And I've actually done this. Mother Jones collected data on the number of deaths from mass shooting incidents. And you know, a lot of people are saying, you know, it's higher than it's ever been. Well, that's true. However, there's so much variation that could very easily happen by chance. Right? I actually did that statistical test that I showed you, where I just swapped the years and said, how often do I see an increasing trend? And I saw an increasing trend about a third of the time. So I was like, okay, I don't think that's a trend. So, and the cause will creep in, right? Because you'll want to say, and financial stories are the worst. Stocks, energy stocks moved, you know, went significantly lower today after, and they never say because they know better than that. They always hedge it. After announcement of weaker employment figures. After doesn't mean anything. But in the mind of the reader, after means because. So don't do it, right? It takes a lot of guts as a journalist to say we don't know. But that's part of, I think, what journalism can learn from science is we can't tell is very often the most honest answer. And if you can't answer these questions, that's what you got to go with.
But can you try to prove the contrary to see if it would it help? For example, in the case of gun violence, to look at which country regulated gun violence and see the immediate result of this. I mean, you wouldn't have 200 countries, but if in all those countries the gun deaths decreased, wouldn't that be an interesting indicator?
Maybe. Unless it's this problem again, right? There may be something that made the countries have higher regulation and made the gun violence decrease. You can never get away from this, right? The short answer is no. You always have to do this. Now, if you can make an argument why there's no other reason that the gun violence levels have changed, then you've got something. But that's a very hard argument to make. And in fact, researchers have been been working on this problem for decades, and it's hard. We're not able to conclusively say that any particular policy or cultural factor has an effect.
You might have countries that manage to decrease gun death. Maybe it's not only by regulating strictly, but it's still worth seeing what has been done.
Yeah, absolutely.
You just take only the country that experienced gun death decrease and see if there is a pattern in the things that they did. And gun control might not be the only thing, but doesn't that say something?
Maybe. You still have to put it through. Look, it doesn't matter what you do. You have to put it through these tests, right? It doesn't matter what it is. It can still be by chance. You can still have the causal structure wrong. It can still generalize wrong. The data can still be bad. It really doesn't matter. You have to ask these questions. I mean, now you're asking. I mean, you're asking a point, which is, can I look in other directions for other types of relationships? Yes, absolutely. But there's nothing that will get you out of responsibility for doing this.
So you could. Oh, I was just thinking that being careful, they said. So it would be like a phrase I hear would be like, gas prices skyrocket today after BP failed to close the well yet again.
Right.
That's like.
Right.
Misleading.
Yeah. And like it's weaselly, right? If you don't know why, then say you don't know why.
Or just don't run the story.
Or don't run the story. All right, so that's we're way over time. Thanks for sticking with me. I hope that was helpful in some way.
We're very depressed right now.
You're very depressed. Well, there's something to be said for embracing the limits of human knowledge, embracing depression. Yeah. No, really. There's. I think part of a big aspect of wisdom is understanding the limits of your knowledge, and so hopefully I've given you a little bit of that. All right. Thank you.
Thank you.
Thanks a lot.